So welcome to lecture 12 of electrical machines course. So last lecture actually we took in the evening and very few of you attended. And in that class we discussed about whatever we are talking last to last class, that is the voltage regulation we talked about, and then we talked about the maximum efficiency criterion, there what is the load point at which the transformer efficiency will be maximum, right? And also we discussed about how to determine the parameters of the transformer, because it is very important to determine the transmission parameters, so in order to find the performance of the transformer. So we saw through some experimental method like open circuit test and the short circuit test, we can find the parameters of the transformer. So in fact, we are discussing the short circuit test, and already we talked about this, right? How the high voltage side is considered to connect the equipments, and then how to take the measurements with the rated current. We need to adjust this voltage in such a way from 0 to gradually increasing the voltage. We'll see that the rated current in the high voltage side will flow, and here also the rated current will flow, so that in the secondary side the short circuit current will also be the rated current. This is low voltage side, but it is rated, and it is also the rated current. And I explained that in order to get this rated current, we need a very small voltage, right? And then we measure the current, voltage, and the power consumed by this circuit. And the equivalent circuit, we have seen that the transformer equivalent circuit will look like this with REH and XEH only, because your shunt branches, that is the core loss component and the magnetizing reactance, will be neglected because the current through the shunt branch will be very less. So that IOC or I5, you can say, right? So I5 will be very less as compared to the rated current, or you can say ISC, right? So therefore we can neglect this IFA, and therefore the shunt branches will be neglected. So, and we have seen how to find the REH, and from this circuit we can find REH will be equal to PSC by ISC square, where PSC is the measured power through the wattmeter. This wattmeter measures the power PSC, because whatever power will be measured by this wattmeter will be nothing but it is consumed in this resistance, okay, REH. So therefore I can write REH equal to PSC by ISC square, and ISC is the nothing but the current measured by this ammeter, okay. And obviously JDH will be, if we'll see the circuit, here is your ammeter, here is your voltmeter, right, and here is your wattmeter. So therefore the voltage measured by this voltmeter will be across this resistance and the inductance. So therefore I can write ISC ZEH will be equal to VSC, and from this I can write ZEH equal to VSC by ISC, right? So now I know REH and ZEH. So that is, these are the referred parameters to high voltage side, right? So this is the resistance, equivalent resistance referred to high voltage side, equivalent impedance referred to the high voltage side. Now from these two parameter I can find XCH. So XCH will be nothing but ZDH square minus REH square square root. This is a series circuit, so very easily I can find XCH. Okay. Now the question is how to find RL and XL, RH and XH separately. because whatever we found now till now is equivalent parameter referred to one side, that is referred to the high voltage side, and if we'll refer it to low voltage side, we can find the low voltage side quantities also. But now the question is how to find these parameters separately, RL, XL, RH, XH. So this we can find assuming that this transformer is optimally designed, considering the copper loss at both the side, copper loss and the reactive drop or reactive loss, both the sides they are equal. That means the copper loss at the high voltage side is equal to the copper loss at the low voltage side. This is the assumption under the optimal design of the transformer, because design part is not involved in your course, so therefore we'll not talk much. So therefore IH square RH will be equal to IL square RL. Okay. Now from this I can find RH equal to, from this equation I can find RH equal to nothing but A square RL, because it will become IL. So your RH will become equal to IL square by IH square into RL. So IL by IL by IH is nothing but, what is that? It is equal to NH by NL. So that will give me equal to A, right? So therefore I can write A square RL. Okay, so that means RH equal to A square RL equal to 0.5 RH. So because they both are equal now, so therefore because we know RH plus A square RL will be equal to REH. Okay, that is the equivalent resistance referred to the high voltage side, and REH is here. We found this REH through the measurement, and now I can substitute this RH equal to, or A square RL equal to RH. So it will become 2RH, that is equal to REH. So RH will be equal to 0.5 REH. Okay, so that is also equal to A square RL. So now from this equation I can find RH and RL individually, right? So I can find RH and RL individually or separately, right? This is how I can segregate now RH and RL from REH. Now coming to the segregation of XH and XL. So similarly we will consider IH square XH will be equal to IL square XL. So this is for optimal design of the transformer. So therefore from this equation I can write XH equal to A square XL equal to 0.5 XH. Okay. So now from this equation I have segregated XH and XL. Both I can find, right? So now I segregated all the components. So now I can uh, write the equivalent circuit, or else I can directly write the exact equivalent circuit of the transformer, because all the parameters are now known. From the open circuit test, in summary, what we can if we'll summarize this open circuit and short circuit test for determining the parameters of the transformer. So the summary is like this. From the open circuit test, we found RCL, right, and XM, XCM, right? Or you can say yes, RCL and XM, XML. Okay, this is from open circuit test we found, right? And from short circuit test we found REH and XCH, and from which we found RL, XL, RH and XH. Okay, so this is from the short circuit test. Okay, so this is the summary. So now we found all the parameters, then we can represent the transformer now through the equivalent circuit parameters. Okay. So now let us do this problem. This is a very simple problem. So the following data were obtained from testing a 48 kVA. Okay, 48 kVA, 4800 is to 240 volt step down transformer. Okay, now the test results are like this. The open circuit test gave us the voltage reading of 240 volt and current reading of 2 ampere and power reading of 120 watt. Similarly, for short circuit test, we found the voltage reading 150 volt and the current reading 10 ampere and the power reading 600 watt. So now what we understood from this test, this open circuit test, as I told, open circuit test is always being conducted at the low voltage side. So therefore you can see here the measured voltage is nothing but it is the rated voltage of the low voltage side, right? 240 volt. So therefore this is conducted at the low voltage side. And similarly, if we'll see the short circuit test, which is conducted at the high voltage side, the rated current of the high voltage side is 10 ampere. If we'll see 4800, 48 kVA by 4800, it will give 10 ampere, right? Okay, now the question is determine the equivalent circuit of the transformer as viewed from the high voltage side. Okay, and also as viewed from the low voltage side. When will that means we need to find the equivalent circuit of the transformer, refer to the high voltage side and refer to the low volt or refer to the low voltage side. Then we can segregate the parameters. Okay. So now let us proceed. The open circuit test and short circuit test results are given here. The voltage, current, and wattmeter readings. Now let us proceed. So you remember these two tests you will do in a single experiment, and you will read these readings you will note from your experiment. Okay. So whenever you will do your experiment in the laboratory, you have to read these observations like this, right? Okay. Now from the open circuit test, I can find RCL because the experiment is being conducted in the low voltage side. So therefore, RCL will be how much? It is 240 square by 120. What is 240? That is nothing but equal to, already we have seen this, VOC square by POC, right? This will give me the RCL, right? And then I can find SOC. SOC is nothing but it is VOC into IOC. Just by multiplying the readings of voltage and current, I found 480 volt ampere. So this is the apparent power that will be supplied from the source during the open circuit test. Now QOC I can find because POC I know from the reading. This is your POC, right? 120 watt, and SOC I know. So QOC will be 480 square. That is nothing but SOC square minus POC square root. So SOC is 480 square minus POC is 120 square root. That gives me 464.76 volt ampere reactive. Right? So reactive power is always represented through var, right? Volt ampere reactive. Okay. And from this I can find XML. So XML, already we have seen this, how to find this. XML is nothing but it is VOC square by QOC. Okay. So that will give me XML. So that is 123.94. Okay. So now if we find A equal to 4800 by 240, that is equal to 20 around this. So next I can refer these quantities to high voltage side also. So now if we'll refer this RCL to high voltage side, then RCH will be nothing but it will be A square RCL. So it will be 192 kilo ohm. And then XMH will be A square XML. That will give me around 49.58 kilo ohm. So these are the referred to high voltage side. These are the parameters. That means the core loss component and the magnetizing component, resistance and reactances, they are referred to the high voltage side. We found 192 kilo ohm and 49.58 kilo ohm. Okay. So now let us find the equivalent circuit, series equivalent circuit parameters uh, using the short circuit test. So you know the short circuit test is conducted at the high voltage side. So therefore the high voltage side equivalent parameters or equivalent resistance will be REH, that will be nothing but equal to PSC by ISC square. So PSC is nothing but this is your PSC 600 watt, right? And ISC is 10 ampere. So therefore 600 by 10 ampere, 10 square, it will give me 6 ohm. Similarly, I can find JDH, that is VSC by ISC. So VSC is 150 and ISC is 10. So 150 by 10, that gives 15 ohm. And from REH and JDH, I can find XEH. So XEH is nothing but equal to JDH square minus REH square root, right? So just substituting the values 15 and 6, we got 13.75 ohm. Okay, so this is your XEH. Now all the high voltage quantities we know, so therefore I can now draw the high voltage circuit equivalent, the equivalent circuit referred to the high voltage side, right? So all the parameters in the high voltage side I know, right? RCH, XMH, REH, XEH. So now this is your circuit when the transformer is viewed from the high voltage side, right? That means all the parameters refer to the high voltage side, right? This is your RCH, this is your XMH, this is your REH, this is your XEH. Okay, so we found the parameters. Now you can draw the equivalent circuit referred to the high voltage side. Similarly, we can find the equivalent circuit referred to the low voltage side. That means when we view the transformer from the low voltage side, we can find that REL will be obviously REH by A square. That means 6 by 20 square. It is coming around 15 milliohm. And XCH will be similarly XCH by A square, it will become 35 milliohm, right? Then, and the low voltage side, I know RCL and XML, I know from the previous side, previous slide, right? So RCL is known and XML is known. RCL is 480 ohm, XML is 123.94 ohm. So now all the parameters in the low voltage side is known. So therefore I can draw the circuit, the equivalent circuit referred to the low voltage side. So this is your equivalent circuit referred to the low voltage side. Okay. Referred to low voltage side. Okay. That means when the transformer is viewed from the low voltage side, the equivalent circuit will look like this. So this is your RCL, this is your XML, this is your REL, this is your XCL. Okay. So now we found the equivalent circuit referred to the low voltage side. Now we need to find the parameters in a segregated manner so that this REL, XCL will be segregated into RL and RH. Okay. And XCL also can be segregated into XL and XH. So already we know the from formula for the optimal design of the transformer, right? So therefore I can write RH equal to 0.5 REH. In this way you can segregate, or in the high voltage side also you can segregate. So this segregation is made in the high voltage side, or you can say for the equivalent circuit referred to the high voltage side. In that circuit we are segregating now. So after segregation I will see both the side, whatever side you segregate, both the result will be same. So if you are segregating RH and RL, XH and XL in the equivalent circuit referred to the high voltage side, that will be same as the segregation in the low voltage side as well. You can test it, right? So now RH will become 0.5 REH, 3 ohm, and your XH will become 0.5 XEH. It will be around 6.88 ohm. So RL will become 0.5 REH by A square, because A square RL is 0.5 REH. So now it is become 0.0075, that is 7.5 milliohm. And XL also becomes 0.5 XEH by A square, it is 17 milliohm. So now if we'll draw the exact equivalent circuit, so segregating the parameters, and if we'll see the transformer is viewed from the high voltage side, we can see from this side, okay, now your magnetizing and core loss component will remain in the high voltage side. So therefore this is your RCH and this is your XMH, right? XMH, and this is your RH, this is your XH, okay, and this is your RL and XL. So this is your exact equivalent circuit, right? When viewed from high voltage side, right? Similarly, you can draw this circuit can be drawn in the fashion that when we view this, it can be drawn in the fashion we can draw exact equivalent circuit viewed from low voltage side. Okay, this can be drawn very easily because these parameters will remain same, only this shunt branch will be shifted to the low voltage side. Okay, this shunt branch will be shifted to the low voltage side for exact equivalent circuit when it is viewed from the low voltage side. Okay, so now this is the problem. Now your two winding transformer almost we have finished. Two winding single phase transformer. Then in the future classes we'll discuss about the three phase transformers, two winding three phase transformers. So before that, let us talk about the auto transformers. So what is an auto transformer? What is the importance of the auto transformer? So auto transformers are real in your laboratory also you'll find the auto transformers, and they're in fact very much useful as variac. That means when we want a variable voltage, we can immediately vary the voltage very quickly, right? And also sometime it is used in the power circuit or power transmission line. It is being used as interconnecting transformers. So interconnecting transformer or we call it is interconnecting transformer, and it is used in the uh, substations that are those are in between long transmission lines, right? So that means there is no need of stepping up or stepping down of the voltage in a huge range. That means if your transformer doesn't require a huge step up and huge step down, that means it is not like generally in the generating end we step up the voltage very high value, right, from 11 kV to 400 kV around at the generating end, right? And again in the distribution end we convert this 400 kV to around 132 kV, right? So there the ratio, the trans ratio here, if you'll find it both transformer, it is very high, and therefore in these cases it is difficult to use the auto transformer. We cannot use. Okay, we'll talk about more why it cannot be used. And when the transformer is interconnecting, that means there is a huge transmission line between two substations. Suppose we have two substations and we have a huge transmission line, that means a lengthy the transmission line is very long. So then in between we need some substation if there is some problem of voltage fluctuation. In order to handle that, we need interconnecting substation, we call it ICT. interconnecting transformer substation, right? So this ICTs plays very important role, and these ICTs are specially designed as auto transformers because auto transformer has a lot of advantage over the two winding transformer. It gives more efficiency and it is less costly, right? So, and it is very useful when the transformation ratio is very less. Transformation ratio is very less, right? So these interconnecting transformers are in fact the turns ratio or the transformation ratio is almost 1. So there is very less variation. Whenever there is a voltage fluctuation, it happens to work, right? But the transformation ratio is 1 almost. So therefore it is very useful. The auto transformers are very useful in ICT, interconnecting transformers. Okay, let us see the auto transformer. Why? Uh, Let us see first the advantage of the auto transformer. So what are the advantage of the auto transformer? So it is a single winding transformer in series and it has two taps in the primary side and two taps in the secondary side. So it has the advantage of it is cheaper in cost than a conventional two winding transformer of similar rating. Okay. And it delivers more power. How it is less cost, we'll see about it. It delivers more power than a two winding transformer of similar physical dimensions. Okay, so for a similar power rating, an auto transformer is more efficient than a two winding transformer. An auto transformer requires lower excitation current than a two winding transformer to establish the same flux. Okay, so for the same flux, the auto transformer requires very less a current. Okay, so you can see here this is an ideal auto transformer. This is in fact a auto transformer which is being found by connecting the two windings of a two winding transformer. Suppose we have a transformer like this. We have a two winding transformer. Okay. And this side is E1, this side is E2, this side is V1, this side is V2. Okay. So now if these two windings are connected in series and I can have two taps at the output, then it will become an auto transformer. So that means in case of two winding transformer, the transformation of voltage and power, it happens through the magnetic coupling circuit, right? But here in case of auto transformer, this transformation happens in both way, inductively as well as conductingly. That means through the conduction process and through the induction process both. But here in case of two winding transformer, the only principle of operation is induction principle, right? Okay. So now let us connect these two windings in series like an auto transformer and see the performance of this auto transformer. So this is an ideal two winding transformer which is connected like an auto transformer, right? So here the primary winding is connected to the secondary winding in series, and now the output is taken at the secondary side across N2. Okay, N2 number of coils, and the input is fed here across both N1 and N2, right? So N1 winding and N2 winding in series, across which we are feeding a voltage that is VA1, right? So therefore I can write VA1 is equal to EA1. So EA1 is across the voltage across the N1 and N2, right? So that is nothing but equal to E1 plus E2. Okay. Similarly, I can write it as VA1 for ideal transformer. I can write VA1, sorry, V1A. 1A is equal to E1A equal to E1 plus E2. Right. Similarly, I can write V2A is equal to E2A, that is equal to nothing but E2. Okay, because this voltage will reflect here, right? And if we'll see the current here is I1A, and here the current is I2A, right? Okay, so let us see these equations, then we'll further. So this interconnection between two windings can have four different structures, right? One structure is this, and another three structures I'll show you. It will be in a different structure, right? So for this structure, so your B1A will be equal to E1A, that is equal to E1 plus E2. V2A will be equal to E2A equal to E2. And from these two equations, if I can find the ratio of V1A to V2A, that will be equal to E1A by E2A, and that will be equal to E1A is nothing but E1 plus E2 by E2. So that will give me N1 plus N2 by N1, right? Okay, because they are all directly proportional to N1. So they are nothing but N1 d phi by dt, N2 d phi by dt. So all will cancel out. So that because they are in the single core, right? So therefore N1 plus N2 by N2. So now 1 plus A. So we have taken here N1 by N2 is equal to A for a two winding transformer, right? Now it will become 1 plus A, that is nothing but equal to AT. AT is your transformation ratio of the auto transformer. A is the transformation ratio of the two winding transformer. Okay. And AT is the transformation ratio of the auto transformer. Now we can see from this relationship AT equal to 1 plus A. That means AT is always greater than A, right? So for the same size of the transformer, we are finding the transformation ratio greater for the auto transformer than the two winding transformer, right? Okay. So again, if we'll see the MMF equation across the two sides, so I1A is passing through both the coils N1 and N2, so therefore N1 plus N2 into I1A, that is equal to N2 I2A. So if I'll find the ratio of I2A by I1A, that will give me N1 plus N2 by N2, that is nothing but the same 1 plus A, that is equal to 80. That means the transformation ratio of the auto transformer 80 is equal to nothing but it is V1A by V2A. That means the primary side voltage of the auto transformer V1A divided by the secondary side voltage V2A of the auto transformer, that is equal to I2A by I1A, right? That means the current at the secondary side divided by current in the primary side I1A, that is equal to 1 plus A. Okay, so A is nothing but it is the transformation ratio of the two winding transformer, as you can see here, right? Okay, so now let us see the power relationship. If we'll now find the apparent power of this auto transformer, then I can write SOA, which is the apparent power of this auto transformer. That will be equal to your V2A into I2A, right? So that means V2A is your output voltage of the transformer and I2A is the output current of the transformer. So therefore it will become your kVA rating or the apparent power of the auto transformer. So if we'll again substitute instead of V2A, I can substitute V1A by 80 because I know V1A by V2A is equal to 80. So V2A will be equal to V1A by 80. Then instead of I2A, I can substitute 80 into I1A. So now I can find V1A into I1A. That means V2A into I2A equal to V1A into I1A. That is nothing but it is the input apparent power. That means input apparent power is equal to output apparent power for an ideal autotransformer, right? Because there is no loss. So therefore, for an ideal autotransformer, we are getting the input power. Input power is equal to the output power, right? Now let us see the relationship between the kVA rating or the apparent power of two winding transformer with the auto transformer. What will be the relationship? So we know that V2A is equal to V2 from this side. You can say V2A is nothing but is equal to E2. Already we know V2A is nothing but equal to E2, right? Or E2A, that is equal to E2, right? That is equal to V2. Okay. Because these cases are ideal, so therefore I can write V2A equal to V2. And your I2A will be equal to 80 I1A. Already I know this relation, right? I2A equal to 80 I1A. So 80 I know is equal to A plus 1 into I1A. Okay. So therefore I2A will be equal to A plus 1 into I1A. Now if we'll write the apparent power for the auto transformer, that is SOA, is nothing but is equal to V2A into I2A. So by substituting V2A equal to V2 and I2A is equal to I1A, so I can write it as equal to V2 into I1A into A plus 1, right? So this I1A here, if we'll see, this I1A is nothing but is equal to I1, because in case of two winding transformer, this I1 under rated condition, this I1 will be equal to I1A, right? Whatever current will flow in the N1 winding, right? Under when it is connected as two winding transformer will be equal to I1A under the rated condition, right? So therefore I can write I1A equal to I1. So therefore it is substituted as I1, right? So therefore I can write it V2 into I1 into A plus 1. Okay. Now I1 I know. So I1 is nothing but is equal to I2 by A. Because I know the relationship in the two winding transformer, I2 by I1 is equal to A. So therefore your I1 is nothing but equal to I2 by A. So I can substitute, in case of I1 I can substitute I2 by A. So therefore your relationship became V2 I2 into A plus 1 by A. Okay. So now V2 I2 is nothing but it is the apparent power output of the two winding transformer. If your two winding transformer is looking like this, already I have shown you the picture, right? So this is your two winding transformer. This is your V1, V2, I1, I2. So then your apparent power output of the two winding transformer will be V2, I2, right? This is your I2. So therefore, instead of V2 I2, I can write the SO, which is the apparent power of the two winding transformer, right? So therefore, the apparent power of the auto transformer will be equal to the apparent power of the apparent power of the two winding transformer multiplied with 1 plus 1 by A, right? So A plus 1 by A is nothing but 1 plus 1 by A. So this is the relationship. That means the apparent power of the auto transformer is equal to the apparent power of the two winding transformer into 1 plus 1 by A. So A is nothing but A is your transformation ratio of the two winding transformer. Okay. Okay, now this is the relationship between the apparent power of an autotransformer with the apparent power of the two winding transformer. That means from this relationship we can see that for the same size of the windings in the two winding transformer, if it is connected as autotransformer, that means we are getting the apparent power of the autotransformer as SO plus SO by A, right? So that means SO is the output of the two winding transformer which we are receiving induction through the principle of induction, right? And this part is received through principle of conduction. Okay. So that means for the same size of the transformer, your auto transformer is giving more output. It is because of the both induction and conduction operation principle, because it is providing the power inductively as well as the through the principle of conduction, right? Because they are connected in series. So through the conduction also it is giving some power, and through the induction also it is giving some power, right? So therefore the rating of the auto transformer is increasing more as compared to the two winding transformer. Okay, so this is one type of connection, and next we'll see another type of connection. So this is the same two winding transformer which is connected in a different manner. Different manner means across the N2. So these two windings are connected in series, right? N1 and N2. And across N2 we are supplying now the voltage V1A. Okay. And we are taking the output across N1 and N2 in series. This is your V2A, right? Okay. So across N1 and N2 we are taking the output and we are connecting a load here. Now if we'll write the equation, how it will look like, your V1, so your V1A will be equal to E2, right? Obviously it will be equal to E2, right? And that is nothing but equal to V2 in case of two winding transformer, and your B2A will be equal to E1 plus E2. That is nothing but V1 plus V2. Now your current I1 is flowing, I1A is flowing in this direction, and I2A is flowing in this direction, right? Okay. So now if we'll uh, find the ratio V1A by V2A, so how I'll write? I'll write E2 by E1 plus E2. Okay. So now it will be 1 by 1 plus A, right? Okay. So 1 by 1 plus A, because E2 if we'll divide in the denominator it will become E1 by E2. So your E1 by E2 is nothing but equal to A. That is the transformation ratio of the two winding transformer. So that is equal to, I can write AT. Okay. So your transformation ratio now it is changing for this structure as compared to the previous structure. Okay. So here the transformation ratio became 1 by 1 plus A. And if we'll consider the current, so if we'll write the current, so your current here I1, so I2A by I1A, I can write it as transformation ratio that is equal to AT. So that will be equal to I2A is for how much? So your I2A is flowing here in E1, right? That means N1, that is nothing but is equal to I1 by, so I1 is how much? I1 is equal to uh, I1A. So I1A is, if I'll write I1A, So I1 is flowing in E2, right? Okay. Sorry, we'll write in this fashion. Considering the MMF across both the sides, so both the windings. So MMF for N2, so I1A into N2, that will be equal to N1 plus N2 into I2A, right? Okay, because I2A is flowing in both the winding N1 and N2, and I1A is flowing in N2 only, right? So therefore I can write uh, N2 into I1A equal to N1 plus N2 into I2A. So from this equation, if we write I2A by I1A, so that will give me N2 by N1 plus N2. So that is nothing but 1 by 1 plus A, which is nothing but equal to 80, right? Okay, so we're finding the transformation ratio same for using the voltage and current relations, right? Now coming to the apparent power. So if we'll find the apparent power of the transformer SOA, so in the output circuit, if we'll write SOA, that is nothing but V2A into I2A. Okay. So your V2A is nothing but, I can write it is V2A is nothing but V1A by AT. Okay. And your I2A is nothing but is equal to I1A into AT. So it will give the same relationship. That means V1A into I1A. That will give me SO input, right? Or S in A. That means the apparent power input is equal to the apparent power output in the autotransformer. Now if we'll find the relationship between the apparent power of the autotransformer and the two winding transformer, so how it will look like? So SOA is equal to, I know, V2A into I2A. So here you can see I2A is nothing but is equal to I1, right? Okay. Here you can see I1 is when the rated current will flow in this circuit as I2A. So that is nothing but is equal to I1, which is flowing in case of two winding transformer, right? So V2A into I1 I can write. So if we'll convert this V2A into V2, right? How I'll write this? So if we'll convert this into V2, so V2A is nothing but it is V2A is your yes, from here V2A is V1 plus V2 V1 plus V2 into I1, right? Okay, so now your V1 plus V2 into I1, and if I can convert V1 in terms of transformation ratio and I1 in terms of I2, V1 in terms of V2 and I1 in terms of I2, then how I can write? So V1 will be nothing but it is AV2 plus V2 into I1 will be nothing but I2 by A, right? Okay. Yes, uh, I2 by I1 equal to A. So therefore I1 equal to I2 by A. So therefore I can write it here as this equation as V2 I2. Let me write it clearly. So it will be equal to V2 I2 into 1 plus A by A. Okay. So that I can write it as SO into 1 plus 1 by A. Okay, so the same relationship we got. SO is the output this is the output power or output apparent power of the two winding transformer, and SO is your output apparent power of the autotransformer, right? So that means the relationship says that SOA is equal to SO plus SO by A. Okay. And A is equal to nothing but N1 by N2. Okay. So that means the output of the autotransformer is always greater than the output of the two winding transformer of the same size, right? Okay. So this is for this kind of structure. Now, if we'll take another two structures, because we can connect the two winding transformer in four different structures. So already two different structures we have discussed. Now, other two different structures are here. You can see here other two different structures. They're presented here below in the below figure. So when we can take our supply voltage, if we'll connect across E2 and E1 and take the output across E1, right? Previously we took the output across E2. So now we are taking output across N1 instead of N2. And another structure we can have is when the input voltage is connected to N1 and we are taking output across N1 and N2, right? So previously in this structure we are saying we are giving the input to the N2, right? And we are taking output across N1 and N2. Here we are giving input to the N1 and we are taking output across. So these are the four different possible combinations or by combining the windings of the two winding transformer, we can have four different structures. So for four different structures, we can derive these equations. So already for two transformers, two types of autotransformer, two different connection of autotransformers, we have seen the equations, and I hope you can derive for these two transformers, right? So for these two connections, I hope you can do the derivation of different equations. So no need to explain further. You can do it in your home because it is possible. It is very easy to do. So you can do it. And your transformation ratio and the kVA rating all will be vary in these four different structures, right? Okay, it will vary always. So now we can see this problem, but this problem will take little time, longer time. So therefore, we'll stop here and we'll discuss this problem in the next class, maybe in the tomorrow class. Okay. So tomorrow we'll discuss this. Okay. So thank you. Thank you very much. We'll stop here.